Hello, continuing with the 2018 Oxford PAT, we got question 18 this time. So the diagram shows two spheres, mass m, suspended from wires of negligible mass, length between the pivot points, and the centres of each sphere is L. Okay, they've marked that on. The two suspension points lie on a horizontal line separated by distance x, which they've marked on. Systems in equilibrium take acceleration due to gravity to be g. Okay, so we can assume that delta x is much less than L and delta x is much less than x. Right, so we're probably going to have some trig small angle stuff going on here. Right, show that the small deflection delta x by which the gravitational force Fg between the spheres will deflect them from the vertical is given by that. Okay, with a approximately equal to, so that fits in even more to how we're going to have some trig approximations. Right, so let's mark on then a few other things on this picture. So we're going to want to have our forces on there. So we've got an mg going downwards, we've got a t going up there, and then we've got this force, which is the force of gravity attracting these two balls together. So we're going to want to do, well, resolving vertically and horizontally. So let's start with that then. So, well, the t cos theta bit is going to be easier. So going vertically, we've got t cos theta equals mg, and then going horizontally, we're going to have that t sine theta is going to be equal to F, and F is the force due to gravity between those two things. So that will be gm squared over, so what's the separation between them? The separation between them is x minus 2 lots of delta x squared. So we've got all of that. What else can we say with this? We've got, I haven't used anything with L yet. Right, L comes in our trig then, doesn't it? Because it will be dx over L is sine theta. So delta x over L is sine theta. That's just doing trig. We've also got, so I've used T and F and mg, delta x. Well, I think I've used everything there. So for small angle, we can also say that sine theta is going to be equal to tan theta for small theta. So let's put that in, because it looks like we're going to, oh, we do have a cos up here. So, but doesn't look, we've got no thetas in here. It doesn't look like we're going to get a 1 minus theta squared type thing that we've got for cos. So let's go with those and see what we can do. So let's create a tan then, seeing as we're saying that's much like sine. So we can divide the second one by the first one. So if that's our second equation, that's our first one. We do 2 divided by 1. That's going to give us that tan theta is going to be equal to gm, because one of those m's will cancel, over g, little g, x minus 2 delta x all squared. And that is going to be roughly equal to sine theta, which is delta x over L. Right, so what are we, has this got all the stuff in it that we want? So delta x, just in terms of x, L, m and g's. So L, yeah, that's going to be fine. So we just have to rearrange this for delta x. So let's go over this side then. So we'll have gml equals g delta x, and then, well, we square out that bracket. So x squared plus 4 delta x squared. Then what we got, minus 4 x delta x. Okay, so that is, I mean, this looks very much like a quadratic formula. So, but we can ignore this actually, this 4, by the time we've expanded that out, right? So let's go for, let's expand it out. So we've got g delta x x squared plus 4 delta x cubed, which is going to be tiny, minus 4x delta x squared. So we can say that for delta x is much less than x, as they told us in the question, we can ignore the delta x cubed term because it's going to be super small. And now we're wanting to solve this for x, so we need to set up a quadratic in delta x. So what are we going to have on all of this? So let's ignore, we've ignored that. So we're going to have 4x. Oh, I've left out g's in these last two terms, haven't I? G there and a g there. Okay, so we've got 4xg delta x squared minus g delta x squared plus gml equals 0. So that means that delta x is going to be equal to gx squared, that's our minus b, plus or minus g squared x to the 4 minus, we got 4, so 16xg gml. Well, everything's in that. 16xg gml. And then we need to divide that by 8xg. Right. So is this getting anywhere near what we actually want? Actually, it does look as though it's getting near what we want because we have got an x over 8 for the first term. Right, okay, they've gone for just a minus, but we'll deal with that in a minute. So this term, if we take the 8xg inside, that will be 8 squared x squared g squared. So the g squareds will cancel. We'll be left with an x squared over 8 squared. So yeah, that's fine. And then we'll have 16 over 64, which is a quarter. We'd have an x and a g on the bottom cancelling with the ones on the top. So yeah, LMG over 4xg. Right, so that's fine. So all we got to deal with is the plus or minus. So why have we got a minus there rather than a plus? What do we know about this that's going to change things around? Right, so yeah, what have we got that's going to change all of this? We can't really mess with, it's going to be m, isn't it? Yeah, as m, if we got no mass, we got no force, and delta x will be 0. So we need that delta x goes to 0 as mass goes to 0. So if the mass is 0, then we've got x over 8 plus or minus x over 8. So we need minus, not plus. We need minus, not plus. Because yeah, otherwise we'd get a quarter of x when there was no mass. Whereas we need it to be 0. Right, that was a lot of work for that first part. I mean, it wasn't massively complicated. It was fiddly algebra. I suppose the difficult bit is getting in your small angle approximation. Once you've spotted that tan and sine can be the same thing, then you're okay. But otherwise, yeah, I'd say that's pretty tough. Right, what else do they want to know? Is that it? Well, that's 7 marks. Right, they haven't got much more to do. We just got 2 marks on the last bit. Oh, and they were saying there, state clearly all assumptions. Well, I think the only assumptions that we had, we had 2 of them. We had the small angle and the ignoring the delta x cubed term, but I actually said those as we went along. So that was good. The spheres are now both electrically charged with the same positively charged Q, positive charge Q, so they're going to be repelling each other as well as attracting each other. How big must Q be so that the wires hang vertically? And they've given us that there. So we're going to need that gm squared over x squared because they're going to be hanging vertically. So that's going to be our gravitational attraction has got to be equal to kq squared over x squared, which is the electrostatic repulsion. And what do we have to do? We have to say how big must Q be? Right, so we can get rid of the x squareds, and we're going to get that Q is going to be equal to m square root of g over k. Right, that was a quick 2-mark finisher, considering how difficult the 7 marks was for the first part. So yeah, they've come straight back out with another really difficult question. But there you go. That's done question 18. Question 19. Consider the circuit above. A filament lamp A consumes an electrical power 100 watts when it alone is connected to a voltage of 100. Right, so if we've got 100 watts from 100 volts, that means the resistance must be 100 ohms. And then for B, we're getting 20 watts from when it's connected alone to the same voltage. So it must have 5 times the resistance. This is all just coming off of power is V squared over R. So that makes it easy. Right, when the switch is closed, which lamp will be brighter and why? Find the ratio of the levels of brightness of the two lamps, assuming their resistances are constant. Assume further that the brightness of the lamp is proportional to the power it consumes. Right, so in this case, the power through A, so A is going to get 1/6 of the voltage because PD divides in proportion to the resistance. So we're going to, for our V squared over R, we're going to have 100 squared over 6 squared is going to be our voltage, and then R is 100. So that gives us 100 over 36 watts. The power for B is going to be, well, we're going to have 5 squared times 100 squared over 6 squared, 6 squared for the voltage, and then multiplied by 500. So that's going to be, well, we've got 500 cancels top and bottom, so we'll have 500 over 36 watts. So B is 5 times brighter. So B 5 times brighter. Is that what I wanted? So which one will be brighter? Yeah, B. Find the ratio. Yeah, 5 times. Yeah, so that's good. How would your answer change if the lamps were wired in parallel? Right, if they're in parallel, they've already told us what wattage they have, because it's the same as connecting them up alone. So it's going to be that A is 5 times brighter because it's the same as wiring them individually. Right, as usual, the circuit question comes up trumps. So it's great when they put in these ones with circuits because they're always so much quicker than the other ones. So yeah, that was nice. Lots of working out space. Oh my word! Right, okay, we've got a book to read here on all of these. Not very. What is it? 7 marks for it, so it's quite a lot. Right, in a crystalline material, planes of symmetry are labelled using triplets of integers. Okay, HKL. For this question, it's not important how it works or what they mean. That's good. Possible to determine these triplets for multiple planes of symmetry. From the knowledge of several such triplets, the microscopic structure of the material can be inferred using these rules. Right, so we've got some rules. I think all the rest of it is just padding. If for all planes, all positive integer values of h, k, and l are possible, then we've got simple cubic. If they add up in that way, then we've got body-centered cubic. And if they're either all odd or all even, then we've got face-centered cubic. Okay, 0 is even. During the analysis of the data, we found these 4 things. What type of lattice? Right, so if for all planes, all positive integer values are possible, but we don't have all of them, so they haven't found those, so it's not all of them, so it can't be the first one. If for all planes, you add them up and you get an even number, right, well, it's not that even then, is it? So it's going to have to be the last one, so it means they've either got to be all even or all odd. So yeah, all odd, all even, all odd. Right, so it's got to be the last one. So this means we're face-centered. Face-centered cubic. Okay, so that was all right. In a material with some form of cubic lattice, the distance d between the planes of symmetry is given by that. Right, so that's just 3d Pythagoras, where a is a constant length, usually of the order of a fraction of a nanometer. Using the formula for D and the data in the table below, determine the best estimate. Right, so they're making the most of this being the first year of having calculators in the exam. So yeah, we're just going to have to put all these things in then. So for the first one, we've got A is going to be equal to 0.224 and then multiplied by the square root of the sum of the squares, so root 3. I'll put all this in the calculator in a minute. And then we're going to have 0.195 times what we got here. That's just going to be 2 times 2. Then we're going to have 0.137 times, so root 8. And then we're going to have 0.117 times root 11. So, well, I suppose we type all of these into the calculator and then take an average on them all. So we've got 0.3880. Then we've got, well, that one's easy, 0.390. I don't need to calculate for that. Then this one comes out at 0.3875 and then 0.3880, which gives an average of, well, let's keep it all in the calculator, 0.38837975, so 0.388 nanometer average. Okay, that was a bit tedious, but there you go. A cube of the material has length L in each dimension, where L is NA and N is a very large number. Pressure is applied to two opposite sides of the cube. Volume remains constant, but one of the cube's dimensions reduces to 2/3 of the length. What is the new length of the deformed object in the other two dimensions? Right, so we've started with L cubed. And we've gone to, what have we gone through? We've gone for 2/3 NA times x squared when we want to know what x is. I think that's right, isn't it? And L is NA. What's the NA doesn't, what's the NA? What's the point of putting all this NA in? Because all we're going to do is say, well, that's L. So all the NA stuff just seems to be a complete waste of time. So we can cancel that with that, and then we'll say that x is going to be L root 3/2. Right, so yeah, I don't know why they were putting all that NA stuff in. That was a waste of time, wasn't it? Right, that was a pretty straightforward question, providing you can read through all of the material and you've got time to do it. I suppose that's the thing. It's quite time consuming reading through all of that stuff, but aside from that, it was pretty easy. Right, question 21. A child of mass m stands on a platform which rotates freely at angular speed omega. Child's centre of mass initially at r0 from the axis of the platform. He's slowly pulling himself closer to the centre. State the minimal force needed to pull the child closer to the centre as a function of the radius of the child's centre of mass. Right, so we need a centripetal force, which is going to be, well, we need a net one, don't we? It needs to be greater than required for that particular radius. So our FR needs to be greater than MR omega squared. Because if it is MR omega squared, we just keep going in the same old circle. So we need a greater force in order to pull it in closer towards the centre. Right. Find a mathematical expression for the work done by the child when it has reached the centre of the platform. Oh, they're giving us a hint here that it's the integral, which is what we're going to do anyway, so that's fine. So yeah, the work done is going to be, when am I going to actually write this? I'm going to stick up here. I think I've taken up too much of the page with the picture and the text. So yeah, we've got to do the integral of f over r, because that's what they've been calling it all here, r's. They've given us the hint in s's, but you know, same old thing. So that is going to be the integral from r0, where it starts, to the end of mr omega squared dr. But of course, with this, we're measuring R going outwards, we're coming inwards, we have to have a negative. So, yep, so that's fine. Into which form of energy is the child's work converted, and what will qualitatively happen to the angular speed omega as the child approaches the center? Right, so the work is going to be converted into kinetic energy, and he's going to start spinning faster and faster. Yeah, this is like the ice skater, isn't it? When they're doing a spin and they pull themselves in and they spin faster and faster and faster. So that's the same thing going on there. All right, that's good. The angular momentum J of the system of child and platform is a conserved quantity. It is defined to be J equals I omega, where I is the moment of inertia of the system, yeah, given by this equation, yeah. IP is the constant moment of inertia of the platform. Find an expression for the angular speed omega as a function of the radius r of the child's center of mass. Right, so we've got I omega, okay, is equal to, what did they say? We've got, let's think about what they've actually asked here. So I omega is equal to, is it really as quick as this? They've given us I mean, which is that. And we need to multiply that by omega. It's only 2 marks, yeah? Find an expression for omega. So omega is going to be equal to, well, I omega was J, wasn't it? So this is J. So we need J over mr squared plus the moment of inertia of the platform. Right, fair enough. Find the total work done by the child when it has reached R0. So we need to, where is our integral? Yeah, where was it? The integral from, well, let's change that around then. So it was mr omega squared. So we can change the limits the other way up to get rid of the minus sign. So we're on mr omega squared was our work done. So, well, we've got mr omega squared is going to be J squared over mr squared plus IP all squared dr. So that's what we're trying to work out. They've given us a hint, which is this. Right, so we need to get it into a format where we've got a plus x squared. And we need, so r is our x squared. So we want to divide this, get rid of that m is more or less what we like. Let's take that m squared outside. So we'll have 0 to r squared, mrj squared over m squared r squared plus ip over m squared, all squared, dr. And is that right? Oh no, we don't have m squared. We just want m, don't we? Because we've taken, yeah, that's right. So that's good. Now we've got to use this. So what have we got then on this? So let's cancel those. The j squared over m bit, we can just put outside. J squared over m. So that leaves us with this, yeah, in the same format. So we're going to have a 2 that we're going to put there. And then we've got the, oh, it's actually done the whole integral. Right, even better. So we're going to have 1, let's put the minus outside, over, I've put the 2 outside already. So we got a plus x squared. So that would be r squared plus ip over m. Right. And we need to evaluate that between R0 and 0. Right, this is quite heavy work. So that is now the, well, I suppose you could change the limits back round again, having this minus sign has been going in and out of this bracket like crazy. So if R is 0, we've got 1 over IP divided by M, so M over IP. And then we'd take off the 1 over R0 squared plus IP over M. Right, so if we put the M at the top, means we need an M there. So that will cancel with that and with that. Have we got much else to say with this? J squared over 2, 1 over IP minus 1 over MR0 squared plus IP. Bit squeezed onto the screen. I probably dropped off the screen. Yeah, right. That was very, very fiddly. I don't like that. I could easily have. I mean, I can't see that I've made a mistake, but it was one of those ones that's so fiddly that it wouldn't surprise me if I had. Not a big fan of that question. It just, yeah, feels more like a slog rather than anything that's insightful. It's nice to have something when you think, oh, I've actually figured something out here. How are we getting on? Have we got more? Oh, this looks like, oh, we're at the, oh no, we have got 2 more questions. So I think I'll leave that video there because this is going on far too long and we've still got potentially 2 long questions left. Yeah, I didn't like that question 21. I thought that was a bit on the fiddly side. Question 20 wasn't great either, but I suppose they have to put in some of those ones where you can read new information and solve things. And yeah, question 19 was nice. Question 18 was really difficult. That was a tough bunch. Yeah, this has turned it into quite a difficult end to the paper, I think, for question 18. These have been some tough ones. But yeah, so if you're getting good marks on these, you should be quite pleased because these are difficult questions. Anyway, I'll come back with the last 2 questions in the next video.